A 3-foot by 4-foot piece of cardboard will be turned into an opened top box by cutting out square corners and bending up the sides. Write a function that describes the volume of the box in terms of the length of the square corner cutouts, and use a graphing calculator to determine the length of the cutouts that will provide the maximum volume. Let's draw a picture. We have a 3-foot by 4-foot piece of cardboard. This is 3, this is 3, this is 4, this is 4, and now we're going to cut out square corner from each side. We're asked to write a function that describes the volume of the box. So remember, we're going to cut out those corners, bend up the sides. And so we'll be bending up along these dotted lines. And we need the volume of that box after we cut out the corners and bend up the sides. Now they tell us we're going to, well, it says write a function that describes the volume of the box in terms of the length of the square corner cutouts. So I'm going to call that length of the square corner cutouts, let me call that x. And so all these little pieces here are width, or length x, I should say. So then this dimension right here is not 4 because we've cut out part of it. In fact, we've cut out x on one side and x on the other, so we now have 4 minus 2x as the remaining length. Similarly, this dimension would be 3 minus 2x. So now we can write the volume as a function of x. After cutting out the corners, the length is 4 minus 2x, the width is 3 minus 2x, and the height is x. And so there's our function. Now, it's not really in completely factored form, it's not in standard form, but it is a polynomial function, and so we should expect it to have maybe a local maximum, a local minimum. We're asked to find what is the maximum volume. Let's talk a little bit about the reasonable domain of this function. What is the minimum x value that can be used here? Well, we have to cut out x. Remember, x, recall, here is the length of the square corners that we're cutting out. So the minimum amount you could cut out is 0. So I'm going to say the minimum x is 0. That's the minimum amount you could cut out. Now the maximum amount you could cut out would be 1.5. If you were to cut out 1.5 from one end, when you think about this, if you were to cut out 1.5, right, that's 1.5, well then you'd have to cut out 1.5 on the other side, and now you've cut out the whole side. And so you would no longer be able to create a volume. You'd no longer have one side to bend up. So the maximum value of x is 1.5. So that's going to help me when I'm graphing on the calculator. All right, so let me put in the function. I have 4 minus 2x by 3 minus 2x by x. And so now when I go to my window, my x minimum is 0 and my x maximum is 1.5. Oops, I hit 2 there. Scale isn't too important. I'll use a scale of 0.1. The y values, those are the volumes. So the minimum volume is 0. The maximum volume is going to be kind of low. I'm just going to go with 10. And the scale, I'm just going to use a scale of 1 there. I'm graphing the function on that window. I do see a maximum on that domain. Calculating the maximum. So the maximum occurs when x is equal to 0.57. So the volume is maximized when the length of the square cutouts is 0.57 inches. Let me just double check that.